So where we were last time was working toward Fourier analysis as a sort of generalization of envelope following. And my hope for today is to actually take a slight detour and fill in some things that I didn't get working last time to just show you how they can be done, and then to go back and rejoin things here. So this is a this is from last time, and this is a sort of one-time. This is a one-channel Fourier analyzer, and the way it works is you take whatever signal that you're going to analyze, which for the sake of what we're doing is just this oscillator, and then you frequency shift it down so that it has a nice low frequency, whatever that might be, and then you low-pass filter it so that only that low frequency gets through, and then you look at it. And looking at it means just picking off its amplitude and its phase. Right? And so what happened here was we took the signal, we frequency shifted it basically by multiplying it by a complex exponential with a negative frequency. And then we low-passed it. So this is the real and imaginary part of a complex signal, if you like. And so we low-pass filtered that, which we can do by low-pass filtering each one separately. And then, just for purposes of seeing it, I took snapshots of it at a specific speed, and then went looking at the amplitude and phase difference, which is to say it's actually just the phase. The phase difference actually between this oscillator and this oscillator, but in fact, when you do this using Fourier analysis, it's just called phase. Okay. And so what you saw when this went on, actually let me reconnect this. So this is just to get us back to where we were 2 weeks ago. So a good thing to do now would be to look at the real and imaginary parts of the signal and just get the magnitude coming out so we can look at that. For some reason I disconnected these, but now I'm going to reconnect them. And let's see now. Give this a nice frequency. Give this some frequency that we'll alias it down by. Start looking at it and see if we're getting something. Oh, amplitude we need. And oh yeah, right. And so now what we get is there's a nice steady amplitude measurement, and then there's phase difference, which is going crazy, and that will keep on going crazy until at some point I get nice and close to the frequency that I'm actually looking at, minus that frequency. And then the thing will quit being crazy and actually give us a nice, solid, steady phase difference. The thing about this is I can find, this will become important in a second. We need to keep this on the screen. Okay. What will become important in a second is the fact that I can actually mistune this thing and still get these zero phase differences. And at least I'm not actually dead sure that will work in this exact case, but we'll see. So first off, I'm going to start making it do its thing, and then I'm just going to see if I can, yeah, there we go. See if I can find another frequency at which the thing does the strobing trick, which is to say, now what's going on is we're taking, this is the old thing about taking a movie of an airplane warming its propellers up. Sometimes you see the propellers going forward and sometimes backward and so on. Right now what I've done is I've chosen a difference in frequency, which is of about 19 hertz, some 19 hertz and change. And that frequency difference turns out to be just the frequency difference so that it slips almost exactly one cycle in this amount of time, 50 milliseconds. And if you work it out, 50 milliseconds is about a 20 hertz frequency, and so that makes sense that by knocking it off 20 hertz I got this answer. So two things to observe here. One is that the speed at which this phase difference is changing gives me a nice accurate estimate of the frequency of this oscillator, and that's the basis of the phase vocoder. Right? That's how a phase vocoder works. And the other thing is it will lie to you, and the way it will lie to you is it will also give you it'll give you the same frequency estimate for a whole bunch of aliased frequencies. Another way to think about that is this frequency here that I gave it, minus whatever, minus 1 over this in hertz. Any multiple of that will show up as the same frequency here, and that's precisely the sampling theorem. because if I just snapshotted this, this phase difference, like 19 hertz, and snapshotted it with this metronome, then I wouldn't see the sound changing at all, or I wouldn't see the phase changing at all. And that's, so in other words, I aliased 19 hertz all the way down to 0 hertz. So the general rule is that if you have spaced a bunch of analyses apart in time by a certain amount, then the frequency estimate that you get, or the phase difference estimate that you get when you wait that amount of time, can be the same value for a whole bunch of different frequencies, and those frequencies are all aliased copies of each other, and using exactly the same rules as foldover uses. This is just foldover. And thinking about this might actually help you understand about foldover too, if you're thinking about that. Okay, meanwhile, what's the measured amplitude of this thing? Well, I put in 1, and I am going to, oh, look at that. I've done something horribly wrong. I should have seen something that was very nearly, oh, sorry. I didn't want to measure that. I wanted to just Hilbert this thing and measure it. That's cool. Okay, let's go back and mess with this. Let's go back and give it something close to the correct frequency. Now let's look and see. Oh, I'm sorry. This is not doing what I expected it to be doing at all. So what I really wanted to be doing was this. Hilbert tilde just straight on this oscillator, and then measuring that amplitude, which is a sort of envelope follower. Yeah, question?
What units are that phase difference in? Is that going from...
Oh, I should have said something about that. Yeah, so the phase, yeah, so what are the, there, my answer. Okay, so what are the units of this phase difference? They are, as arctangent puts it out, they are in radians, which is to say 2 pi of them is a full circle. But I divided by pi so that I would get numbers from -1 to 1.
Okay.
Oh, arctangent normally puts out, most arctangents put out values between -pi and +pi. That's a convention that's usually used. Yeah, it's ugly because in computer music the most convenient unit for phase is in cycles, so that you make something that goes from 0 to 1 and does that over one cycle. But mathematically you need to be going from 0 to 2 pi, and so there are frequently factors of 2 pi that creep into this thing at bad, undesirable moments. Yeah.
Yeah, is the idea with the phase vocoder then that you're trying to get rid of like discontinuities in phase between your windows?
Sort of. Let's see, they're not discontinuities so much as they are the fact that if you, any signal is changing in time, if you wait too long between measurements, you don't get a sense of what the true shape is.
Okay.
And so it's discontinuities, but it's really discontinuities in the timing of the photographs that you take of the thing.
Okay.
And yeah, and furthermore, you don't even have to put up with it. You can just say, I want to do a phase vocoder, and I want to start a new window every sample, and then you will get, everything will be happening at the full sample rate, and then you'll never get fold over, or at least you'll only get the fold over that you got when you sampled the signal originally. And I'm going to try to make an example of that, but I might fail later on. So I'm going to save this. Oh, right. So now the other thing that was going on here was sometimes in general you will probably expect to see more than one frequency going on at once, and so then you get, what's going on here? Oh, I need to turn it on, and then you get stuff. So it's not the case that when you add 2 oscillators together, you're really going to get the if you want to actually look at these oscillators and not have them mix up, you have to do a low-pass filtering step somewhere. So just the straight old Hilbert-based estimate of amplitude only worked when you went ahead and low-passed the thing before you tab wrote it. And then if I do that, I'll get this wiggly effect. And in fact, I want to do that just to get us back to where we were last week in order to make a corrective. So I'm going to put in my nice lop 20 to be comparable to the other picture. And now we've got this going. wiggly, but not so wiggly that it's completely messed up. And now if we start looking at that here, interesting stuff will happen. So let's add this into this analysis here too. Oh, sorry, I gotta just connect it everywhere. You know what, I should just make an explicit plus for the sake of being clear. Plus. So now what's going on is we have two oscillators, we're adding them, just for the purpose of making sure we can actually distinguish things from each other. And having added them then, I'm going to throw those into all these places. Right. Okay, now what we got is we're analyzing a thing that has two tones. One of these tones, 440, actually got aliased down to something that we can look at, and it's and one way of saying that is it actually made it through the low-pass filter after we aliased it down. The other one was 880, and so it only got aliased down to 440, and then these low-pass filters almost got rid of it. So that wiggliness is the fact that we didn't quite get rid of it, but we at least almost did. And now, as these things get less and less distant from each other, the amplitude measurement gets crazier in both of these ways of doing it. Okay, now, and then an issue last time was, well, why don't you just low pass the thing until this thing quits moving? And the answer was, yeah, but then when you low passed it that much, the thing doesn't react quickly. So are there good ways of getting around this trade-off between between speed and wiggliness? And the answer is sometimes you can do pretty well that way. And the way you do it is this. Let's see. How am I going to do this? Because this is now, okay, I need to sample the signal again. So I will get, oh, I need a whole chart recorder. Well, all right, let's sample it and just stick it on a slider so that we can see what it's doing. Snapshot, metronome. I want to make it a little faster, though. Oh, actually 50 is pretty fast. That's fine. Okay, and then I'll get one of these things. Turn it on. Yeah, okay. That's bad because I chose a bad range. There we go. All right. So now we have now we have a troubled envelope follower. Is everyone following what I'm doing so far? This is partly recovering stuff that happened 2 weeks ago. Okay. Now here is a thing which I think the best approach to is just get it, because I tried to redo this out of pure thought and failed. So what I'm going to do is I'm going to just grab this patch, or should I? Yeah. Grab this patch and put it here. Except I think now I should do a save as. And now I'm going to save on top of this one. How about that? Yeah. And then we don't need this anymore. We'll maybe go back to this later, but we can go open the other patch. And then we can get this out of here. Nope, can't do that. Alright. So what do you do with this thing? Well, a possible answer is the following. You could take this value and treat it as a range of values. In other words, it's what you see is that isn't changing is that this is always between this between down here and up here, say, right? Whatever that difference is. And then what you can do is say, well, all right, when it goes above the top of that range, we'll pull the range up, and then when it goes down below the bottom of that range, we'll pull the range down. So what happens here is there's an input for the size of the range that we're interested in. And then what we do is we say, all right, $F1 is going to be what goes in. $F2 is going to be what just came out. And you can't actually pull this thing up here, because then how would you ever delete it? So you have to actually use some other object. So I just put a float here just to be able to make this connection. Right. Actually, it would be clearer. I don't know which is clearer. Maybe it's clearer like that. Okay. So what we're going to do is we're going to take the new value and look at our last output and take the smaller of those two things. What that means is if the new value is smaller than the last output, we go down. Otherwise, we stay the same. Right. And then we'll take the new output and the new input and subtract the size of the band that we're interested in. And if that is lower than the our previous output, then we pull the band up. So this part of the step is push the band down if we are lower than the previous value. That gives us a new previous value. And here what we do is we say, compare the previous value again to the incoming value minus the band. And if the incoming value minus the band is lower, then is higher, then we pull it up. So that means we take the maximum of the two values. So the minimum means optionally decrease it, and the maximum means optionally increase it. And then if the size of the band is 0, we're not doing anything, because we're looking at if F1 is less than F2, we take it down, and if F1 is greater than F2, we take it up. That's just letting the value straight through. But if we make the band actually have some width, like whatever that width is, let's give it a small width and just start easing it up. Ooh, look at that. Oh, I already gave it 0.1. So I gave it a width of 0.1, and now the thing is not wiggling at all. And theoretically now, if I can change the amplitude of the sinusoid, and it will react quickly. But it reacts quickly, but also gives me a rock-stable answer as well. This is of use anytime you have a noisy signal. And now I've got to just show you something about, because I don't have a nice chart recorder for showing this, although can I do it with this? Let's see. Let's make this thing last a second. And then let's just run the snapshot output right into the tab right. This is a little bit wrong, but do it anyway. Alright, let's see if this works. Oh, that's not going to work because that's too fast. Okay, so now we're seeing, that's interesting. Oh yeah, okay, good. So this is now dirty envelope follower output. Okay. Now what it should be possible to do is, for instance, rather than using a metronome, what I can do is do something that turns this thing on suddenly, or makes it change suddenly. And then shows us, oh, yeah, right, this is going to show us the output with a delay of a second. Okay, so now I'm going to turn this back on. Whatever that went to, and whack this tab right once at the same time, and then see how the thing reacts. Okay, so now what we got is, we see the speed of reaction, which took us this amount of time, and then we see the wiggliness of the thing. In fact, to make that clearer, let's make the low pass a little lower. Let's turn this off. And then do another. Huh. All right, that should have been more sluggish looking, but odd. All right, well, that's just what it is. Seeing steadiness, and then we say go up, and all right. Okay, so then now we want the thing to be faster so that it'll rise faster. So let's make it have a nice low pass of, I don't know, 30. Still not Still not extremely fast, but it's not so bad. Oh, in fact, I can make the metronome. I can make this metronome go faster, so you can see more detail. Ah, there it is. Okay, so there's the rise shape, and then there's the horrible "I can't do it"ness of the input follower, right? Okay. Now we start applying smoothing, or whatever this kind of smoothing is. I don't think it has a name. And what I should do is just do this by eye until this thing stops wiggling. Like that. Now I'll turn it off, and this is still going. Okay, I guess we can just turn it back on and see what happens. And ta-da! Now you see that it's a lie. It's a very good lie, but it's really not strictly the truth. It didn't really rise quickly to a correct value and then stay rock solid. Instead, it rose quickly to something that was almost the correct value, but then it took it a moment or two for the jittering to finally push it all the way up to the range that it was in. So this will work fine for pushing things with noisy MIDI sliders and things like that. You can use this thing to fix that jittering problem that a MIDI slider sometimes gives you. But the gotcha is that it's like a loose linkage in a car. You won't really get turned exactly the direction you're going at until the thing settles in still. But still, you can imagine using this to drive an oscillator. It would be a great deal less unpleasant than if the thing was just bouncing around all over the place, as it was before I did this smoothing operation. Okay, questions about what's going on here? And this expert, my best advice to you is just just copy this thing down from a patch in which it's working, because if you try to do this by pure thought, you'll get the max and min mixed up, or plus and minus, and then you will be lost for a half hour, and it's better just to, once it's been done once, just copy it. Okay. Now, going from there, what I want to do is go back to frequency domain analysis, but in this but now pulling out the actual objects that do it, the FFT objects. So now what we're going to be doing is not exactly what we were doing before, which was to do this sort of informal low-pass filtering of an alias signal, but actually to go ahead and do that for real. Let's see, we don't need that anymore. And 280 jitter. And what I want to do this is to pull out one of the help windows to start with. So this is just a cheat, but it's a pretty good cheat, because if you know where to get this, you can remind yourself about all these truths. So the first PD help file, which is about Fourier analysis, is basically just a demonstration clearly in real and imaginary parts of what a Fourier analysis of a sound does. It's not doing the resynthesis, it's just doing the analysis. And I'm not going to attempt to talk about resynthesis, although these examples move immediately to resynthesis after the first example goes by. So what I'll do is I'll save this and then start diverging from it pretty soon, or pretty quickly. So let's do a save as and get this back where I want it to be. And this is going to be 2B Fourier, actually RFFT. Okay, so here oh, it's FFT. Okay, fine. Here what did we say? The object that's being used is the fast Fourier transform object. In PD, there's a real FFT object and there's a complex FFT object, and 99% of the times you use the real FFT object. The difference is that it takes a real signal coming in, and so it does only half the computation, and so it's cheaper and effectively does the same thing, or it does all that you actually need. But here, for the sake of pedagogy, we're actually taking the overall complex FFT, and what happens is this object takes a block of data coming in. So pure data is always operating on blocks of data. By default, the blocks are 64 elements long, and no one actually ever really does a 64-point FFT for practical purposes. So this is only what's the right word? This is only pedagogical or didactic in purpose. But the idea here is to start looking at what happens when you start pumping the Fourier transform with oscillators. And now, since this is 64 samples long, or rather, since the bit of sinusoid that we examine is 64 samples long, the lowest frequency sinusoid that will actually fit inside that analysis is sample rate divided by 64, which is typically something like, typically in the upper 600s or low 700s, somewhere in there, depending on what sample rate you've got. What I've got is, well, 64, oh right, I get to choose a frequency. I'm going to choose 1 for now. So 1 over 64 times the sample rate is 689 hertz. That's the frequency at which one cycle will fit in the analysis window of 64 samples. And that's kind of ridiculous. That no one would ever actually analyze something using a fundamental frequency this high, but except us right now. Okay. And having done that, I will simply go ahead and talk about a frequency that's 5 times higher, because then you'll see something that's not at the very beginning of the table. Yeah, question?
I'm a little confused actually. What's the difference between the top frequency number, the 1, and the frequency in hertz?
Oh, okay. Yeah, actually. Okay, so this frequency is being multiplied by sample rate divided by 64. So the way engineers talk about this is the frequency in bins. And for some reason, a channel of the Fourier transform analysis is called a bin. Really what it is a frequency band. And so this is the width of the frequency bands. And what this means, unfortunately, is that the bottom frequency band is a DC band that's this wide. So it goes from minus 1700, oh, I'm sorry, wait, one band. I need to turn this to 1 to show you this is the length of an individual band. So this DC component here, which is at 0 right now, is looking at the looking at frequencies from about minus 340 to positive 340, because they're straddling 0. That, by the way, is a terrible misfortune in some respects. Although, well, I don't want to go into it. So because the Fourier transform, as it's usually practiced, actually has 0 as a frequency, instead of having the first band starting at 0, you get a couple of weird things that happen at DC and at the Nyquist frequency that make it look like everything isn't perfectly symmetrical the way you would wish it. But we're just going to go ahead and do it the way it's conventionally done, because convention is more important than mathematics for us right now. Okay, so I give it this frequency, which is the middle of the first band. Oh, I should draw a picture. Picture time. So here's the picture drawer, and so now what's happening is in frequency. Okay, let's just try to do this nicely. Finally discover that you can actually make segments here. Okay. So the way frequency bins work is there's a 0 frequency, and then there is a frequency which is whatever that was, 680 hertz. And then there's twice that. Oh, let's call that what's the usual? Can't remember what the usual thing is, so I'm going to call that F0. And then this is going to be 2F0, and so on like that. And by the way, I should have mentioned, and I'm going to now cheat. Woohoo, no, that was a bad cheat. Let's see. I'm going to cheat and actually allow for negative frequencies, because that will make things clearer. There is the first, this is the first output of the Fourier thing, but the last output, which is also the minus first output, is whatever happens at frequency minus F0. And in fact, it continues like that, and it also continues in the other direction. And it doesn't ever stop, but it repeats. So the truth is that the Nyquist frequency is the same thing as the frequency 0, because the Nyquist frequency, sorry, the sample rate is the same frequency as the frequency 0, not the Nyquist. And what that means is if you have a signal that's a sinusoid that's going at the sample rate, then every time you sample it, you'll see the same value, because you've waited exactly a period at the sample rate. And so you'll see the same thing as if you just put DC in. So So 0 is the same thing, or is the same frequency for practical purposes as the sample rate that we have. And so what is going on here in this particular case is the sample rate divided by 64 is about 680 hertz. And that's what I mean by F0. Okay. And just working that around, the 64th one of these things is the one that's going to be back at 0. So you can also think of these things as existing on a circle. In fact, for some purposes, it's actually better to think about this as being on a circle. And usually by default, by convention, you would put the 0 frequency here, and then you would put Nyquist here, and then you would put sample rate back where you had 0. Okay, so this is another way of thinking about the frequency, about these frequencies, and in that case you would see 16 of these things per quarter circle. 1, 2, 3, 4. I won't draw them all, but those are all frequency points at which we don't put the bands, but put the boundaries between the bands. So there is a frequency band between 0 and F0, and so on like that. Yeah?
What happens to the frequencies within the map? Do they get averaged to get yield one?
Sort of. Yeah. It's worse than that. So you put frequencies in, and theoretically, any sinusoid that you put into this analysis should put energy in the band that its frequency lies in. But in fact, it's sloppy, and the frequency also spills out into adjoining bands as well. And I'll have a picture for that later on, I hope. Okay. So now going back to the, actually let me draw another picture here before I go back, which is this picture. Oh no, I want to show you what happens first. So now we're going to start analyzing sinusoids, and so this number here is there to hold the frequency in bands or in bins. So if I say 1, it's in the middle of the first bin. Oh, right. And here's what's confusing about this. The bands are shaped like this. Or bins, if you want. In fact, I'm drawing them as if they actually were bins in the sense of a box that you put things in. So this is what the actual bins look like, from minus a half F0 to positive, and so on like that. Okay. So what this is saying is that if I give it a frequency of F0, we're landing smack in the middle of not the first band, which is the band that's 0, but the second band, which is the 1 band. And that's what we're doing here. I'm saying 1, which is giving me F0, which is then landing right in the middle of the first band. Now, what the tables are showing is the outputs of the real and imaginary parts of the analysis. And those real and imaginary parts are precisely closed it. Let's see. Open it again. Are precisely these numbers here. Sorry, these numbers here, where we low pass filtered a frequency shifted copy of the signal going in. There's one difference, which is this: the way you do the low pass filter. Oh, sorry. Yeah, I'll do it this way. The way you do the low pass filter is by taking the incoming signal. Remember to just dot it. So we take some incoming signal, which is whatever it might be, and then we window it, as we say, which is we take a certain amount of the window, or sorry, amount of the signal, and we call that a window. Oops. Sorry, I should be switching into ASCII and typing these things out, but somehow putting the pen down and getting to the keyboard and back is too messy for me. Okay. All right. So what is the window? Well, in this case, the window is 64 samples of data, but it's whatever it is. And then we can say, well, the frequency of the first bin is in fact the frequency which has the property that one cycle of it fits in the window. And then a thing that we can say about that is, well, then if we took another window analysis later, we would see exactly the same thing in it. And another thing that we could say is, this analysis is the analysis of a periodic signal that fits within this window and is then repeated forever. In other words, this is taken to be one cycle of a waveform, and what the Fourier analysis does, in one way of thinking of it, is it tells us what the strength is of all of the overtones of this waveform. And if the waveform is a sinusoid, if it's either cosine, as I've written here, or sine, then there's only a first harmonic, and so we should only get one. We should only see energy in one place. But if I draw a complex waveform here, then it will have harmonics in general, and those harmonics will have strengths, which are shown by the strengths of the signals that get through these filters, or rather, these frequency-shifted filters. So how do we filter? Well, the way we filter is we frequency shift the thing down, and then we just sum everything that's in the window after it's been frequency shifted. So summing everything is a low-pass filter. If you ever really want to know what the DC component of a real signal is, from the beginning of time to the end of time, you simply sum every single value, or integrate every single value over time, and that gives you a number which is the DC component of that signal forever, right? Including, power supply, being powered up and down, all the things that might contribute to DC are going to be there. Here, if it's a finite length signal, you don't have to integrate it or add it up forever. You can only add it up for one cycle of it, because you know that at that point it repeats. And here I'm slightly oversimplifying, because you would have to normalize by the number that you had, and I'm forgetting that little issue. Okay, so if you want to know what the low frequency content of this window is, you just add all the components up. Another way of thinking about that is, if what was in this window consisted of a thing that had a bunch of partials, so the 0th partial, the first partial, the second partial, and so on, the only one of these that adds up to a non-zero number is the 0th partial. All the others, because they go positive and negative, cancel themselves out and they add up to 0. So if someone gives you a complex waveform that is a sum of simple sinusoids, so if summing that gives you this waveform, then if you want to know what the DC component of that thing is, you just add all of the elements of this function, add all 64 of these numbers, and divide by 64 to normalize, and that will give you the DC strength of this signal. And then if you want to know the strength of the first harmonic, frequency shift it down so that it becomes DC, and in doing so you frequency shift DC down to minus a frequency, so it now is wiggling around. And then once you've done that, you can add all those values up, and then you will get the strength of the first harmonic. So to get the strength of the first harmonic, shift it down to the 0th, and then add everybody up, and then you've got that strength. And none of the other harmonics are going to get in there. Yeah?
Frequency shifting, can you elaborate on how you frequency shift?
Oh, so frequency shifting is exactly this operation here. In other words, it's multiplying by it's using single sideband modulation to multiply the thing down to where it has a frequency of 0. Or in equations, I'll give it to you in the equation. So the equation is this. This thing, if you regard it as a complex signal, is e to the I, call this frequency omega, e to the I omega t. And so what we're doing here is we're multiplying the signal that we have by e to the minus I omega t. So the actual truth of the matter is this. How am I going to do this. I'm just gonna have sloppy penmanship for now. So we're going to assume that we are going to be looking at a signal which is cosine of. I need two frequencies. I need the true frequency, which I'm going to call omega, like that. And then I'm going to try to look at it using a test frequency of omega 0. So that'll be another number, right? So this thing, by the way, is equal to 1/2 times e to the I omega t plus e to the minus I omega t. And then if I took that and multiplied it, actually, let's say divided it by e to the I omega 0 t, then I get 1/2. Let's go back. Okay, I'm going to just show you the positive one first. E to the I omega minus omega 0 t plus another term. The other term actually is e to the I minus omega 0 t. But this is the term that has a nearly zero frequency. Furthermore, if we're talking about doing analysis as in this window, or actually just analysis of a repeating figure, then what we do is we pretend that these omegas are exactly all going to be multiples of the fundamental frequency of that the signal is repeating at, right? And that's the bin frequency, if you like. So we can't just have any old frequency the way we can in sound. We can only have frequencies which are multiples of this window size. And in that case, each one of those things we pick off by subtracting itself exactly. And that gives us 1/2 times e to the I times nothing, which is 1/2, because e to the nothing is 1. And then we just harvest it. We just add up all the numbers and divide actually by 64, which gives us 1/2, because the strength of the positive frequency component is in fact only 1/2. And now we can quickly verify, save this, now we can quickly verify that in fact our FFT object is telling us the truth. So what it's telling us here, okay, now just because we're who we are, I can do this. Let's go here and say, give me a fatter, I don't know what. Oops. Is that going to fit? Sort of. All right. All right. What should I really do? I should be reasonable and say 600. So since we got 64 points, let's make it 640. Hit it. All right. This is good. And meanwhile, same thing down here. Properties. 640. All right, now we can be happy. Okay, I don't know whether I should keep this comment around or not, but I will for now. Okay, so now what we see is we're putting in the thing which has a frequency of 1 unit, which is putting it smack in the middle of the first bin. The bin number 1 counting from 0. So this is bin 0 and this is bin 1. And what it lit up was 2 places. It lit up bin number 1 and it lit up bin number -1. So here again, the way frequencies are organized is 0 is the first bin, which is the 0th bin if you like, and then the first bin is here, and then it goes around until it reaches almost 0 again. And that's a -1 bin, and then it wraps. So that's a way of saying that this over here is -1 bin. All right. And now it's saying that there's energy here, which is the 1/2 e to the I omega t term, and this is now 1/2 times e to the I minus I omega 0. So these two peaks correspond to the fact that the cosine that I showed you here has 2 true frequency components, and each of which has a strength of 1/2. Okay. Questions about? Is it working for you for me to be shifting back and forth between pictures like this, or is that jarring you? Okay, great. Because that could be jarring. Okay, so now if I say how about a frequency of 2? Then it just, oh yeah, so there's an error here, but it's round off error. It's not this big at all. And now what we're seeing is 0, 1, 2 and 0, minus 1, minus 2 both get energy. All right. Now the next thing to know about is this. Different things happen depending on what phase the signal has. And what I've done in this test bed is fixed it so that you can actually set the phase at the outset. So for instance, if I want it to be sine, I would make this be minus a quarter. How about positive 3/4? So we'll say 75. And now all of a sudden, ooh, I think I need to do this one. No, I'm not sure. I'll leave it like this. Okay, so now what happened is, instead of the energy being in the real part, it's now saying the energy all lives in the imaginary part. And furthermore, this bin got a negative number and this bin got a positive number. All right, so what's going on there is this. There's another equation about trig, which is sine of omega t. It's the same thing as the cosine of omega minus pi over 2 times t. Sorry, that needs to be a parenthesis. Okay, but another way of saying it is that this is equal to 1 over 2i times e to the I omega t minus e to the minus I omega t. In other words, in sine, the two things have opposite SIGN sign, opposite polarity. And furthermore, when you do that, you have to divide by 2i. Or, to put it another way, this thing has amplitudes which are 1 over 2i and minus 1 over 2i. And then it turns out that 1 over 2i is the same thing as minus I over 2. And so that's why I see minus 1/2 here. Because this is the imaginary part, which is everything that you multiply by I. And now something hilarious happens, because as I change the phase from from 0, which is cosine, to say 25, which is minus sine, oops, I see the energy go from the real part to the imaginary part, and it does that over the first quarter cycle. And now we're looking at minus sine, and then another quarter cycle later, so that we're a half cycle in, we're looking at minus cosine, and then another quarter cycle in, we're looking at plus sine. And then if we go all the way through to 100, it's back to where it was at the beginning. So what we're doing here is we're changing the phase of the signal that we're analyzing. So this is exactly the same situation as we had here when we were looking at the real and imaginary parts of a low-pass filtered version of this sinusoid, or this pair of sinusoids. It was the same deal where we got two numbers, the real part and the imaginary part, and if we wanted to know whether it was sine or cosine, we had to figure out the argument of this thing as a complex number, or the angle of the complex number. And if we wanted to know the strength of the thing, we had to take the magnitude of the complex number. So that, now I have to go back and make another picture. And I've run out of space. I'm going to save this, and then I'm going to do a save as. Okay, and my labeling is going to be horrible, but I'll just do it. Okay. So here the picture is something like this. If this is the real axis, and this is the imaginary axis, and if you have some amplitude out here, which I'll just call capital A, and which you can describe as a vector which points out to this point, angle A, then there are two things to think about here. This is the phase, or you also call this the argument of the number A, the amplitude A, and then this this thing, which is the radius. Now I'm having trouble because I wrote this in. Okay, good. This thing here is the magnitude. All right, let's get us onto the board here. Yeah. All right. So if I tell you the phase and magnitude of an amplitude, then you can determine the entire amplitude. This is also what people are talking about when they say polar form as opposed to rectangular form. The rectangular form is to report what the real part is, which is the cosine component of this amplitude, and the imaginary part is the sine component of this complex amplitude. And if this is confusing you, then it's just because it's confusing. So in general, then, if I were to analyze a signal, and if the signal looked like this, that would give me an amplitude which was purely real, like that. And if the signal looked like this, sorry, this is this, except it is starting here, a quarter of a cycle before the thing even started, or if you like, starting 3/4 of the cycle here. So this is sine, and if you analyze this, you should get an amplitude that looks like that. So what comes out of the FFT, the Fourier analysis, is not frequencies, they are amplitudes. They're amplitudes of the sound at the frequency, which is the frequency of the channel or bin of the Fourier transform that we're looking at, or Fourier analysis that we're looking at. Questions about this? I feel like I must have just confused everybody badly, but everyone's so too confused to even utter a question. Okay, well, I'll just make it worse. Now what I'm going to do is I'm going to show you what happens when you do this. I'm going to give it a frequency which is halfway between two of the frequencies that I wanted. So I'm going to make it just start out as cosine, but I'm going to give it. Whoops. Yeah. Okay. There we go. I'm going to slap a cycle and a half of this cosine into the window, and then ask the question. Well, okay, cool. That means that we should put. What is the frequency? Well, the frequency is 1.5. It's halfway between this frequency and the frequency of the second bin, which is the second harmonic of this thing. Right? But there's another way of thinking about that, which is these two things, cosine and sine. If you just copy them end to end, you would get a nice clean tone. This thing, if you copied it end to end, can I do this? Gives you badness. Oops. Hey, how did that happen? Wow. Okay. Uh-oh. All right, I don't know what I just did, and I don't like it. But at least it lets me alone once I've finished drawing the thing. Can I just draw now? Yes, good. Okay, so this is what it looks like when you take this signal and just make a couple of copies of it. And the badness is that it has a discontinuity at the end of each cycle. And so if you played this thing, it wouldn't sound like a nice sine tone at all. It would sound like, well, it would sound, you'd hear primarily a sawtooth wave, because what you really hear is one discontinuity every sample. This thing is actually a sawtooth wave plus another wiggly thing, and the wiggly thing that is quiet compared to the sawtooth wave, so it's, for legal purposes, this is a sawtooth wave. Okay, save. And so, of course, then when you take that and analyze it using Fourier analysis, so not this example, but this example. So I'm now going to say, well, give me 1.5 cycles per window, please. And then I get a horror show. First off, the phase is not, well, phase works out differently, but that's all right. The other thing is, I didn't, I told it to center the thing right between this bin and this bin, right in the middle. And instead it gave me energy in this bin and a whole bunch of other energy as well. And this is generally going to be true. In fact, I'm going to jack it to 10.5. It's the same shape anywhere that's halfway between two bins. And this shape is actually, roughly speaking, this is a hyperbola, 1 over x shape. F of x is 1 over x. These things are going off as 1 over x in strength, and that will be very, very audible. And it doesn't look like much, but in terms of audibility, these nice high frequencies are your ear's favorite place for listening for overtones, because that's how speech works. And so you will hear something that's very, very different from a sinusoid if you took this thing and played it repeatedly as a sound. And so the Fourier analysis is only telling us the truth about what's in that window. In fact, for the purposes of Fourier analysis, so now going back to the drawing, for purposes of Fourier analysis, when it sees this thing, it doesn't have any way of knowing whether the outside looks like that or whether the outside actually looks like a nice sine tone at the wrong frequency. Because it doesn't get to see outside of its window, it doesn't know whether it's the one or the other. And the most reasonable choice from one point of view to make would be, let's just assume it's a single cycle of a repeating waveform. I will try to formulate a thought about that later, about why couldn't you just have a bunch of basis functions like this that captured the idea that you might actually have a different value at the beginning of the window as at the end. You might actually have a better set of basis functions than Fourier analysis. And the answer is that exists, and for purposes of analyzing sound it's not so great, but for other kinds of analysis it turns out to be really good. Or rather, audio signal sound, like sound is in snatching a bit of audio signal and using functions like this to analyze it, doesn't work. But if you're analyzing, say, a spectrum to try to reduce an amplitude spectrum to try to get information out of it, it actually might be a better model than periodic functions. But for right now, we're just assuming periodicity, and the assumption is falling horribly wrong, and then we're going to deal with practical ways of getting around that horrible wrongness. Okay. Another thing about this is, and here I have to turn off the synchronization. Okay, so a thing that I haven't told you about this is that this receive blah blah snap, this is actually putting out a bang every time an analysis starts. And what that is doing is bashing the phase of this oscillator so that it's actually getting bashed to the same value every single analysis that's being made. If I unhook this, then I will get sometimes one phase and sometimes another. At this point now, I'm at a frequency of which 10.5 periods fits in a window. And so half the time we're going to start with the thing starting at 1, and half the time we're going to start with the thing at -1, or something like that. And so I get different phases out depending on when I happen to do the analysis. Better yet, if I just go back to a real frequency, like here's 10, or 10 bins, and now I'll take that and very slightly detune it. Then I get the same kind of picture as I got when I did the heterodyning analysis of the single sinusoid. In other words, now that I'm making the frequency that is going in is slightly different from the frequency of analysis, so that the phase is processing is different from analysis to analysis, then I can actually see what the detuning is by looking at how fast this thing is wiggling around.
So in that particular case, when you chose a number, a frequency value that isn't an integer, you would only get imaginary parts, or you saw the 1 over x?
Oh, right. So at this, okay, yeah, I can't actually show both those in the same picture, because if I detuned this to like 10.5, then this thing would be changing so quickly that you wouldn't be able to see the change anymore.
Oh, okay.
So I have to be very close to a bin frequency so that you can actually see this beating effect. But at the same time, if you want to see the frequency spilling effect, then I have to detune it enough so that we get spill, and that's a different picture. That's a picture. Well, so if I say 10 10.4, say, instead of 10.5, I just get different. Sometimes it looks real. I mean, sometimes it looks cosine, and sometimes it looks sine, and etc. Right? But then if I looked at the magnitude of this thing, it would all be stable. All right. Other questions about that? It gets more interesting. If you think this is interesting, it gets more so. Okay. By the way, these are positive frequencies, these are negative frequencies, and the Nyquist is right in the middle. And in fact, one thing that you might care about is, in fact, everything over here is just the negative of what's happening over here. Is that really true? It's the negative complex conjugate, which I think means, no, it is the positive complex conjugate, which means everything here is what it is there, and everything here is negative what it is there. But whatever it is, if I told you what the first half of the table was, you could tell me what the second half of the table was. But I'd have to tell you the Nyquist and the DC component. And then there's another funny thing that happens, which is that the DC component here is always real. Because I'm analyzing a real signal, and the DC component is just the sum of all the values. You can never actually get energy in the imaginary part of a real signal at DC. And the same thing at Nyquist. So Nyquist and DC are real, and the rest of these things are all complex valued. So the total amount of information here is there are 64 numbers of unique information. There's bin 0 and bin 32, and each one of those has only a real value. And then there are the 31 bins from bin 1 to bin 31. Yeah, that's 31 bins. And each one of those has a complex valued signal, which gives you 2 numbers. So actually there's 64 numbers here, but it's like 1 number and then 2, 2, 2, 2, 2, 2, and then 1 again in terms of information. And the way people stay sane doing these things is they just blow off DC and the Nyquist frequency altogether. Unless you're trying to prove something, which, you know, in a paper, in which case you have to throw everything in. If you're just trying to make music, just forget about DC and forget about the Nyquist, because they're not that important anyway, for at least these purposes. Okay. Now, so several things are going on here. One is we actually have a way of measuring the exact frequency of a sound, or of a sinusoid if we want, because we can measure how fast the phase is changing. That's interesting. Except remember that I showed you a situation where 2 different frequencies gave us the same phase precession, right? And so there's a thing to worry about there, which is sometimes called phase unwrapping. But I'll show you that in a way that shouldn't be too horribly difficult to deal with. And the other thing is, depending on how we happen to be tuned compared to the frequency of analysis of the Fourier transform, we either got something nice and ruly like this, or we got something horribly unruly like this. And those are such radically different results that a good analysis technique might want to give us something that is a little bit more resembling between those 2 different situations. So the way we deal with those things is through overlap control and through windowing. And that's the next matter to take up when we're doing Fourier analysis. So what I should do now is show you how that works out. And to do this, let's see, I'm going to save that. Oh, I better, for purposes of sanity, I'll save it with this thing connected. If I connect, this is the phase locking. If I connect that, then we're actually setting the phase by hand as opposed to just letting the phase drift. So I'm going to leave it like that, but then save as. Then I'm going to do a save as and go back to leaving the phase moving around. So here we're going to say 2D Fft Windows. So here what we're going to do is do the FFT. So there's some PD lore here. We're going to do the FFT in a sub-window so that we can control the window size and overlap of the analyses. So right now what's happening, since we're just doing it in PD without doing any blocking, is that everything is 64 samples a block by default, and that's not a good setting for doing anything audio. So what we should do is get in here and let's see, this is no longer relevant. In fact, almost none of this will be relevant anymore. I'm going to keep this around. We're no longer going to have any phase, whatever you call it, phase bashing. I don't need this. Now what we're going to do is make a sub patch. So we say PD, and I usually just say FFT for the name of the sub patch. And here what we're going to do is we're going to block it to some slightly larger number of samples. 256 is actually almost 256 is the smallest Fourier transform you'll ever make in real life, and it's just large enough that you can sort of see things going on that I have to show you next. Is that true? Well, let's see what happens there. Okay, so now what we're going to do is say there's going to be an inlet which is going to pick up this sinusoid like this. And then in here I'm going to say FFT. In fact, we could even say real FFT at this point. Real FFT is like the complex FFT, except it only populates the first bit of it. So now what I'm going to do is make this be 256 points. Later I'm going to make it 128, but I'll make it 256 for now. Ugh, no. Get rid of this, and these tab rights can go in here, and they can even be now the wonderful tab send object. And what did I call these things? $0 real. $0 imaginary. Now let's see if we're doing this. Yeah. Oh, yeah. I've neglected one thing, which is that the FFT is. Oh, several things are wrong here. Why is this not showing me anything? Oh, because I said imaginary. This is easier to look at only for the reason that I didn't worry about normalization this time. So in the original example, I can't remember how I did it, but somehow these numbers coming out were actual sums of, and sums are the sum of a half all the way through 64 samples is 32. So these numbers are rather large coming out of FFT. In fact, here we're doing a 256 point Fourier transform, and so the numbers are ranging up to 128 in value. And that's kind of a little ugly. You don't see it, but some of these points are actually going outside the window. Okay. Now what we would like is for well, first off, there's several things we would like. One thing that we would like very much is to be able to just see the that's interesting. Is just to see the overall amplitude of this thing. I'm not going to try to show you the overall phase because that's going to be bashing around badly, but the magnitude, as I should call it, I'm going to call it magnitude. Everything else can be the same. This we get by same thing as before, except now I'm going to just to be easy on us, I'm going to say x per tilde square root of $f1 times $f1 plus $f2 times $f2. Close paren. What did I get? Oh, I'm sorry, you're not supposed to use f's in this context, you use v's for vectors. And now I'll take that and tab send that into $0 magnitude. And now we get the absolute value of 1 over x, basically. And this thing has the property that it almost doesn't change at all. It changes very slightly with time, but not anything like the way these things are changing. These things are hopping around rather arbitrarily, whereas this thing is basically behaving itself pretty well.
Is
Yeah.
that like the root means, we just did like the root mean squared?
Yes. Not the root mean squared, but the root of the square sum. So if I were taking root mean square of those numbers, it's just two numbers going in, right? So the mean square would be a half of the sum of the squares instead of the sum of the squares. So here we're taking the RMS, the root mean square. You do say root mean square. No, it's just taking the magnitude, taking the linear magnitude of the function. And now we still have the property that, oh right, sample rate over, now a bin is a sample rate over 256. So we still have, ooh, yuck. Yeah, we still have the property that if we give it something that is something that's right on a bin, we get one thing, and if we take it off a bin, we get something else. Now the RFFT object doesn't bother to populate the second half of the table at all. And that would cause difficulties if there weren't also an RIFFT object that will put the thing together and only look at the first half in order to do all these computations. And for that reason, I don't really need 256 points anymore. I only need 129 to be really all-inclusive, including the Nyquist frequency. And hopefully that's got us again to a place where we can almost see what's going on just by looking at the things. All right, so these things are nice and stable, and these things are just going all over the place because there's phase going on too. Okay, and it is still the case that if I get myself right on a frequency, I get a nice stable result, and if I get off of the frequency, then I get this, whatever you call this effect. Right. Now what we can do is this. Let's go back to a nice frequency. By the way, this I believe these tables are ranged vertically to go from -32 to 32. Oh, -64 to 64. Okay, which was appropriate for the 64 window. And now that I've quadrupled the window, things are getting out of range. But I'm not going to worry about that so much. But here, the magnitude really, it only makes sense to report positive values. So I'm going to make it go from say 128 to nothing. And now we see that the thing gave me a 128 as magnitude, and now if I say different frequency, then it only reaches up to something smaller than 128 anyway. It's a number you can compute, but there's pi in there and stuff, so I'm not going to tell you exactly what that number is. Okay, so now we've got a situation where we get sometimes a nice clean peak, and sometimes we get a very broad, messy peak. Okay. So what do we do about that? Well, the answer is going back over to, going back over to the pictures now. What you then do is you window the thing, and what that means is, and now I have to draw on a larger scale, I think. So I'm going to look at this horrible function, which has 10.5 cycles in it. Let's do it like that. It's not enough axis there. Okay. Then what we're going to do is we're going to window it like this. In other words, we're going to multiply it by a thing which fixes it so that it doesn't have this jarring buzzing sound at the end of the signal. So if we looked at this as a signal, it would look something like it would look like a pulse. It would look like nothing at the beginning, nothing at the end, and sinusoid in the middle. Okay. And how could we think about that? Well, one thing that we could say is if we suppose we go back to the idea where we're just going to take the thing and, no, I don't want to do that. We're just going to go back and alias the thing so that it gives us a constant value out. So the signal just looks like a constant. Then when we window it, we just get the window. So if we analyze a constant function, we just get the window. And analyzing a constant function is something that we always are sort of almost doing, because the whole idea is we're going to alias whatever the sinusoid is down to 0 frequency before we analyze it. Or as part of the analysis, either way you can think of it. Well, in that case, you can think about what this thing is, and what it you just get this window out. And what is this window? Well, first off, it has a name. This is called the Hahn window. DSP people sometimes call this the Hanning window, but that's kind of a stupid, lame pun, so Hahn window is probably the correct thing to call it. And the Hahn window, it goes up to 1 in the middle, and it's down to 0 at the ends. So there's an average value, which is a half, and it's 1/2 plus, sorry, 1/2 minus cosine. So here's what it is: 1/2 of 1 minus cosine of. Now I need to give this thing a name. This frequency. So the frequency of that corresponds to 1 bin. And I've already used omega naught, so what's a good... Alright, I'm just going to use the first letter that comes to mind, which is A. Oops. Oh, in fact, if I were talking about this, which I am, in terms of continuous time, then I really need to put the 2 pi in there. And in that way of thinking, this time interval goes from 0 to 1 over A. 1 over A. In other words, if A is a frequency, or yeah, that's true. If A is the angular frequency, then the period of that is 1 over A. So why is this that? Well, okay, this is just one of the functions that people most frequently use to squash down the ends of a signal in order to analyze it. The good things about the signal are it's of course 0 at the 2 ends. It's not just 0, but its slope is 0 at the 2 ends. So it actually approaches 0 quadratically instead of just linearly. And yet and all of its energy, or all of its mass, is sitting in the middle. That's a good thing. And furthermore, just because of the form of this thing, you can see what frequencies are in it. It has frequencies of 0 and then plus or minus the analysis frequency, plus or minus 1 bin. So A here is actually the bin frequency. It's the sample rate over, in digital, this is the sample rate over the number of points. Which is usually n. And that's the same computation that we did in order to try to figure out what frequencies to pump that oscillator with when we were looking at it the first time. Okay. Well, this thing itself has a spectrum because it looks like this, and the spectrum of it looks precisely like this. I can tell you exactly what the spectrum of this thing is. It has a half, and that's at frequency 0. And then there's a frequency of plus A and a frequency of minus A, and at those 2 points it has a strength of minus 1/4. So plus 1/2 at DC and minus 1/4 at A and minus A. And then if you took that and aliased it by multiplying it by a real sinusoid, you would get a similar kind of pattern, except you would get it aliased to some other frequency. So to see that, save, move over. What are we doing? Yes, we're good. Sorry, I'm trying to think about what the best way of proceeding is. I think the best way to do this now is this. we say, I'm gonna make a, you know what, the best way to do this is actually to just make the thing. So I'm gonna say PD on, this is something I do a lot, so I'll just do it. Okay, so let's make a nice array. So this is going to be called, put array, and the array is going to be $0. I'm using $0 so that you can have two of these patches opened at once and they won't fight. And it's going to have the same size as the analysis window. So the tables where we're looking at the spectra are only 129 points now, but this has to be the entire length of the analysis. Okay, and everything else is good. And now what I'm going to do is I'm going to make myself a nice oscillator, and I'm going to feed it sample rate divided by 256. That will be the frequency, and of course I have to whack this in order to get that to happen. So let's make ourselves a nice button. This will be good for now. Oh, wait. Oh, that's the frequency, and now we'll just take this thing and tab right it. We don't have to be doing this constantly, so I'm just going to do it once. Tab right tilde $0 Han. That needs a bang too. Set the frequency and blammo. Nothing. Oh, right. No. That is what didn't happen. Did anything happen at all? Yes. And we're. Oh, it looks like we're. Actually, I don't know what's going on. Oh, no, I really don't know what's going on. Oh, yeah, the range is crazy. Now I want the range to be, for now, I want the range to be, no, the range is fine. Alright. Oh, the problem is you don't use cosine, you use oscillator to make this thing. Alright, there it is. Okay, so now we're picking up cosines inside this window, but of course we need to fix it so that the thing has a known phase at the outset. So the way we do that is, right when we start the tab right, we also send a message to send the cosine to 0 phase, like this. And now it's fine, except it's sort of upside down. So now what we got to do, various ways of doing this, but like I could give it a phase of a half, and that would be hot dogging a little bit. But what I really want to do is multiply this thing. Oops. Multiply it by minus a half, so that it only has an amplitude of a half and is upside down. Now, why did I have that? Oh, times tilde. Yeah. All right. So now we've got something that if we just add a half to it, will go from 0 to 1 back to 0. So let's add a half to it. Ta-da, Han window. Okay, now that we've got a Han window, we can take this FFT analysis and say, okay, before we even take the FFT, let us do a tab receive $0 Han and multiply that by the inlet. And now, what does the analysis look like? Oh, yeah. Now, okay, I'll stick it in the middle of a bin frequency. And now what we see is, depending on how you normalize it, you can think of this as 1, but if I'm pulling a fast one there, it's actually 128. But here what we see is a half, a quarter, and a quarter. Oh, actually what we see here is some sineness and some cosineness, but whatever it is, so there's some phase there that we don't know about, which is just whatever the phase of this thing happens to be. And furthermore, everything that happens has a center, has an energy in the center frequency, which is the exact frequency of the sinusoid I'm looking at, And it has two adjoining frequencies, or has energy in the two adjoining frequencies. And the amplitude that reaches the two adjoining frequencies is a half of the amplitude of the middle. And furthermore, they're exactly 1/2 cycle out of phase of the middle. Okay. And now, if I were to detune this slightly, these phases would start changing in time, but these numbers, these magnitudes, would be rock solid. So for instance, 10.001. Well, it's kind of a mess, but anyway, you can see these things are all jumping around, but these things are rock solid. Okay, so now I'll go back to 10. And furthermore, now what happens when we start changing the frequency? Well, when we change the frequency, the energy essentially leapfrogs, and most of the energy, like depending on how you count it, all but 0.3% of the amplitude sits in, all but 3% of the amplitude, not 0.3, sits in 4 bins, which are the 4 bins which are closest to the center frequency of the, or the true frequency of the oscillator we're looking at. So a special case, if we're, the worst possible case is right between 2 center frequencies, which is right on the edge between 2 things. We get, by symmetry, we should get the same thing on both sides of the bin. So there are actually 2 numbers here that are equal, and then 2 other numbers which are lit up, and then 2 other numbers which are part of what we call the tail. And now as this number changes, we see the energy gradually moving from channel to channel, but in such a way that it never lights up more than 4 points at a time, if we're willing to ignore the slight little bit of tail behavior here that we try to pretend we don't hear. Okay. So this is now a Han-windowed analysis, and it is, yeah.
And then in that case, there's no overlap, right? Are those 4 points related to overlapping points?
Oh, that's a different issue.
Okay.
But that'll be a thing. Okay. Yes. Yeah, I haven't actually worked on overlap yet. That's the next step. Because right now still I made the windows be bigger, but they're still end to end.
Do the points represent spaces within that frequency band or in neighboring?
I guess they represent energy in the neighboring frequency bands, right? Yeah. Yeah.
I'm a little confused. Like when you multiplied that window, can you show how you multiplied it?
Oh, yeah. I actually went quickly over something. Okay, so tab receive and tab send are these things that just dump things, either grab things out of the table just repeatedly every single block, or else dump things into a table every block. So it's there. So tab receive is almost an oscillator, except it's a stupid one because all it does is just copy the table end to end without ceasing. And then all I'm doing is just taking that and multiplying it by the inlet. This becomes useful when we start making overlap, because when we overlap it, this thing will come out still every time, even though it's overlapping samples. But I think it's time for a break, so I'll get that going after the break. I can just start in, I think. Okay, so I'll just start in. And, the good thing about all this is that as soon as you've learned it, you can forget it. And anyway, every time you actually think you understand Fourier analysis, when you come back a year later, you'll realize that you didn't really understand it after all, and then you will find a new way of understanding it, and this will just kind of repeat for the first 4 iterations, or at least that's the way I got it. So by the time you've had to scratch your head over this material and try to understand it 4 times in 4 different years, then you've actually got it down and can do things without getting confused, maybe. So here is here's the next thing I should tell you about this stuff. Okay. So what you've seen is that this Hahn window kind of lights up four bins of the transform. All I'm going to do is close this window, get back to the window. Where's the window? Oh, yeah, I don't think we're going to use this anymore, so let's leave it. So here's where we actually made the window. Now I'm just going to goof off a little bit and just see what happens when you just start messing with the window. So I'm messing with the window, right? And now I'm getting perfectly good analysis again, which actually looks a lot smoother than it was before. And furthermore, this also reacts in a decent way to change. Oh, look at this. Okay, I'll explain that in a second. But I can go sweeping up and down frequency, and this thing actually does a perfectly reasonable job of maintaining its same shape. The fatter the window I make. But the problem with this is, of course, the fatter the window I make, the more bins I'm lighting up with a single sinusoid, and therefore the further away you're going to need another sinusoid to be in order not to get in trouble with them together. So as before, let's see, we made this. So I'm just going to make another oscillator and make them fight. And the other oscillator I'll give some other frequency, like 10-ish. Right? And now everything is cool. Oh, look. Okay, so everything is cool. What happened now is we have two different peaks, and they have, except for this spot right here, they're pretty kind of stable. And now what happens when I make the frequency difference less than whatever that was, 12.5 bins. So let's make this 15 now. Now they're overlapping. And furthermore, they are not standing still, because at this point the relative phase of the two oscillators is different from window to window, or from analysis to analysis. And as a result, sometimes in the intermediate frequencies they are interfering constructively and sometimes destructively. And I think you can get, so right now what you're getting is the thing sometimes you get kind of the sum of the two, and sometimes you get the two fighting against each other going to zero right between the two. Right? So it's still the case that things are decently stable right at the peak of these two things, because each of their peaks is actually slightly past the tail of the other one, so that it's not actually getting into the peak even though it's getting into the rest of it. And then even that quits being true as I get closer and closer to just having the same frequency. So now I just have, it's not even fighting now, but it should be sometimes giving you one answer and sometimes giving you another answer, just depending on how the phase works out. Whereas if I, let's see, let me say, let's have this be 20 and this be 24. Except I really want things partway between bins to be more realistic. Okay. So now they're overlapping like I'll get out still. And now if I go back and just recompute the Hahn window, then they get pretty well resolved. Okay. Well, could you make these things skinnier? The answer is you sort of can. I can make this thing look like this. And that slightly decreased the bandwidth of the window, and that actually made these peaks a little bit narrower than they were for the Hahn window, at the expense of having more junk outside of the window's own regions of influence. Because now, suppose this were a half cosine, the slope wouldn't be zero anymore, and so there would be more of a buzzy sound if you regarded that as a repeating waveform. Okay, so you could do this, but it doesn't really terribly work well. And then you can also do this, and then it doesn't work terribly well in the other way, which is that the peaks get fatter. So let's move this way out of the way. And furthermore, we can make these peaks as fat as we want. Well, that's as high as it wanted me to get. So, I could just make this almost a pulse. And then I get nice big fat peaks there that are useless for separating anything from anything else. So, so basically, the longer the duration this thing is, the more frequency resolution we get when we do the analysis. And that's usually called the Heisenberg uncertainty principle. What it is that spread in frequency times spread in time is bounded below by a certain number, and the number is one thing in continuous land and another thing in discrete land. Here, what happens when you're time windowing things with Hahn windows is that this width is, if I get off of bins that you'll see in general, this width is lighting 4 bins up, and in fact it isn't exactly 4 bins wide. So the bandwidth of the Hahn window is 4 times the frequency of the analysis. It's not a really good constant. You would wish that the bandwidth would only be equal to the width of a bin, but you just can't get there. In fact, you can't even get close to there. Okay, now there's another picture that helps or might help explain this. Actually, before I leave this, let me go back to that other wonderful example. Trying to make it approximately symmetric. Notice that everything is still going plus and minus in sign here. When you take the magnitudes, everything is cool, but in fact it's the case that neighboring bins of the FFT, when you're looking at a sinusoid, are always exactly, well, not exactly, but about 180 degrees out of phase from each other. And there is a reason for that, which I will try to make clear when I go over to the blackboard. Yeah?
What happened if you had a square wave as an analysis window? See now, so it's a
Oh,
possibility for some-
cool. Yeah, let's do it. Actually, what would happen then is exactly what we saw in the very first picture, which is 1 over x drop off. Oh, this one's right on a bin, so you just see everything perfect. And here, we're between bins, and so you see this picture that's the same as you saw before we started applying the window at all. So rectangular window is the same thing as no window. And in fact, rectangular pulse window, oh yeah, gives us a thing which is a function we all know, which is sine x over x. Now the cinch function, about which I should probably try to talk in a second. This is a little sloppy. I should be doing this analytically instead of with the mouse. But now as I make the pulse wider, you'll see that this thing gets narrower, and the side lobes gradually pull in and get denser and denser. So see those lobes there? The width of those lobes is 1 over the width of this thing that I make, this pulse. Okay, so now I have to show you some pictures about what this looks like analytically. So the first thing I should show you, let's see, let's save this and do a save as, and this will be C now. Save and go away. Start over. Okay, so so a thing that you saw there was a function of frequency which looks something like this. Here is frequency of 0, here's a frequency of 1 bin, here's a frequency of 2 bins, and so on like that. This is -1, and so on. This function is sine, of pi, what do I want this to be called? A frequency. Pi f over, and then usually you put the pi in again. Oh. Yeah, this is good. Okay, so this as a limit turns out to be 1, and when f is 1 or 2 or 3 or so on, sine of pi times anything is 0, and you're not dividing by 0 anymore, so there's no limit to take. You just see it actually really just get 0. Furthermore, right here, it's worth knowing what this value is. So this value is pi times 1.5. Well, the sine of that is -1. And then, so it's -1 over pi times 3/2. So it is minus 2/3 pi. And this is 2/5 of pi And the next one would be 2/7 of pi. So minus 2/3 of, is this possible? This is just 1, right? Is this number less than 1? It's not. So something is horribly wrong in what I just did here. Oh, pi is in the denominator. That's what's wrong. So what I should do is pick this up, throw it in the denominator. Same here. Ta-da. Okay, now we're back to reality. Okay, and these numbers I got just by applying this formula. Now, where did this thing come from? Okay, so this is the analytical formula of this thing that I just showed you here when I took a rectangle function to the single sinusoid and then made an FFT of it. And notice still that, oh, it's not true anymore. Okay, a thing that isn't true. Oh, right. I don't have the proper plus and minus sign alternation because I didn't put the pulse right in the middle. If I put the pulse right in the middle as I had it before, then you'll see that same pattern of alternating sign up here. Okay. Now, so why do you see that stuff? Well, the reason you see that stuff is this. If I, in the time domain, that's to say as a signal, if I took a nice pulse, skinny pulse, and then started multiplying it by complex exponentials and then integrating it, what would I get? Well, the first thing I would get is I would multiply it by the value 1, or the whatever you say, basis signal 1, like that. And so what I would get at frequency 0 is positive whatever the area of this thing is. So let's just call it 1 for fun. Right? Then, suppose I now ask for that times cosine. Well, actually, if I why cosine? Why not? I should be talking about a complex exponential here. Then I will get a thing which looks like minus 1, nearly minus 1, because the test function by which I alias this thing knocks this thing around to minus its own phase. Right? Now, this is only true if I put this thing in the middle and if I regard 0 phase as being at the beginning of the window. And if you adopt the convention that all phases are counted as 0 in the middle of the window instead of at the beginning, which you'll see in some mathematics textbooks, then you don't get this alternating in sign. But it's in DSP, it's universally taken to be 0 phase at the beginning of the window, not in the middle. As a result of which, then you see this plus and minus alternation going on. Furthermore, you can even ask about fractional frequencies. So you could say, well, what if I just took this thing and analyzed it? And now I'll try to draw this as if it were actually a complex exponential now. So let's draw real and imaginary axes, and then this is time. And I'll start at 1 and wrap, sorry, 1's over here. Start at 1 and start wrapping around like that. And back to 1 there. Oops, oh, that's a whole cycle, and that's the cycle that got down to -1 there. Okay, but now I'll do just a fraction of a cycle. Ooh, I can't do it in this perspective. Let's start here and say 0 frequency would do that, but a positive frequency would start wrapping around more and more around until finally a frequency of 1 wraps all the way around. But a frequency of, say, a half is only going to wrap around halfway down to here, and here it's going to be only 1/4 cycle. So if I look at what should be there at 1/2, which is not actually a point at which the FFT is going to report the frequency, but I can pretend it is anyway, I'm going to see that this actually has a what's the right word, an amplitude of I, positive I or negative I? Negative I, because we're going to divide by this thing. So then how do I draw negative I? I put it down here. Okay, so what I need to do now, with apologies, is I have to switch axes. I'm going to call this the real axis and this the imaginary axis. Oop, except the imaginary axis probably needs to be over this way, pointing toward us. Okay, there's imaginary, there's real. Okay, now one looks like pointing straight up, so that looks like real. And then imaginary is going to be pointing out like, whoops, pointing out, all right, pointing out. So in that case, minus I doesn't look like this, minus I is pointing this way. Sorry, I'm trying to make a three-dimensional graph in 2 dimensions, and of course, I'm doomed to failure, but the only thing sporting is to try anyway. Okay. So then here it looks like I, then minus 1, then minus I, and then 1 again. Okay, so at 0 frequency it's 1, at frequency 1 it's minus 1, at frequency 2 it's positive 1, and halfway between it's I and minus I. So it's actually describing a spiral that looks like this. And this is actually true regardless of what width we give this pulse. As long as we center the pulse in the middle, it's going to be the case by symmetry that the phase of whatever we see is going to be spiraling around in such a way that it spirals all the way around only after 2 bins of frequency. So if we only look at this at integer bins, we see 1, minus 1, 1, minus 1, and so on. That's the explanation of why in this picture, even when you applied the Hahn window like we did here, you see alternating positive and negative numbers here. That's because the phases that are in the successive bins are actually negatives of each other. And that's because of the symmetry around the middle of the window of the Hahn window. Okay. And the other thing to say about that is this. Now when we analyze a pulse whose width is the entire frame, okay, so this is narrow pulse, and this is wide pulse. Oops. Well, the wide pulse is horrible. Sorry. Oh, I don't care anymore. Okay. The wide pulse is, in fact, just the entire width of the analysis window, so it's actually just the function 1, or it's DC. So we know exactly what DC analysis looks like, except if we start thinking about what DC looks like here, in allowing ourselves to look at frequencies that are between the frequencies of the actual analysis, then we get something interesting, which is we get amplitudes that look like sine x over x, and phases that look by symmetry like that again. So if you try to put that picture together, and this is, you just take a battery that's putting out 1.5 volts and stick it into an FFT object. This is what you get, assuming your converter can deal with batteries, right? So you get a thing which, if described in terms of continuous frequency, looks like sine x over x in magnitude, which means I'll take a center frequency and then mark off bins from the center frequency, and I will try to get the thing to go through. Okay, so about sine x over x function, the middle lobe is 2 bins wide, and the side lobes, as we call them, are only 1 bin wide apiece, right? Because it misses hitting 0 at 0. That's the good spot, right? So what we do here is we draw a spiral that that hits 0 at each of these points, but also negates itself in phase each time around. So it negates itself in phase for 2 reasons. One is because it goes negative here and positive there, and it negates its phase again because of this reason. except for here, you'll see the thing actually wiggle around. So what it does is it wiggles around, hitting 0 at the appropriate places, getting gradually bigger until finally it gets to this point, and then it does one big twist. And then it starts wiggling around in the opposite sense. So this is actually what the Fourier... Okay, this is again making this be real and this be imaginary. This is what the Fourier transform of that thing looks like as a function of continuous frequency. And then if you take this thing and look at it at the frequencies of analysis, it's not in general the case that you're going to hit omega, because omega is whatever the center frequency is that we're measuring. Right. So here what we're doing is we're taking a thing which is a thing which has center frequency omega, but which has amplitude, complex X amplitude that's constant, and then we're saying that this is what the analysis of that looks like. And furthermore, if we look at integers, well, okay, we'll see a number here. This thing lit up to a value of 1, and then it hits 0 at each of these other integers. But then if I assume that the integers that I'm looking at are somewhere else, I'm going to see something different, which is actual numbers. Non-zero numbers that are non-zero all the way up and down. Because I'll catch these loops, and these loops actually are only going off as roughly 1 over n, 2 over 5 pi, and so on. Let me do that. Okay. Now, what did the Hahn window do to improve the situation? Well, what the Hahn window did was it took this picture. Now, let's see. I'm going to make a duplicate of this picture. Wish me luck. Takes this thing and then adds to it copies of itself at half amplitude and 180 degrees out of phase. And what that accomplishes is, in magnitude, that gives us something like this. Oops. Gets up to a half here and goes through 0 there, 0 there, 0 there, and so on. And then it also goes through 0 here. So what I'm doing is I'm drawing another cinch function that is centered 1 bin north of the one that I showed you first. And then there's one that's also amplitude of a half, which is 1 bin further south. And now if you look at the sum of those three things, what you get is something which is not 2 bins wide, but 4 bins wide that looks like this. This is 1/2 because it's this, because it's this peak right here. This is 1/4, so I didn't draw this very well. This is 1/4, which is half this height, because that's from this peak here. And then there was the peak over there. And furthermore, once you get off those 3, past 2, then you will see that the 3 side lobes are out of phase. And they're out of phase in a way that goes off as 1 over n cubed, I think, when you add them up. So it goes off much, much faster than the 1 over n that a rectangular window goes off, because these side lobes are actually canceling each other out increasingly well as the denominators get bigger. And you can work that out, but it turns out that this one here is 34 dB down, if I remember right. Maybe it's 37 dB down. I can't remember which. It's 30-something dB down from the center peak here. And furthermore, if this is the way the window shape looks like in terms of frequency, if this is centered in some frequency which is not a frequency at which I'm analyzing, then perhaps the frequencies at which I'm analyzing are something like this. 2, 3, 4. And then I should expect to see 4 channels of the FFT light up. And then I should see a little bit of action because of the side lobes that don't cancel each other perfectly. And this explains why the width of the analysis that you get when you apply the Hahn window is 4 bins wide in the FFT. So then when can you resolve 2 peaks using an FFT? The answer is, roughly speaking, well, okay. I keep forgetting I can just do this. If I have a sinusoid going at omega 1 and another sinusoid going at omega 2, this thing lights up frequencies that go from omega 2 minus 2 up to omega 2 plus 2. This one goes up to omega 1 plus 2. So you want the difference from omega 1 to omega 2 to be at least 4 bins for these 2 frequencies to be perfectly resolved by the Fourier analysis. Yeah, I didn't draw that terribly. I didn't draw that quite to scale, but you get the idea. What does that translate to? That translates to such bad numbers that it's actually amazing that people get away with this. Specifically, when you, if you decide that you want the time duration of analysis to be almost inaudibly short amount of time, for instance, if you use a 1024 point FFT, then the analysis is about a 40th of a second because, or a 44th of a second because you use typically 44 kilohertz sample rate to do the analysis. So a 44th of a second, it's like 23 milliseconds if I'm, no, wait, it's 20 something milliseconds, 22-ish. That's a decently short amount of time. Fine, but then if you go back and look at it the other way, that you're repeating actually 43 times a second-ish at 44K1. And that means that this frequency, the analysis frequency here, the bin frequency, is 43 hertz, which means 4 times that is, whatever that is, 160 hertz. So anything below about G below middle C, you're going to have trouble resolving using a 1024 point FFT. Now, it's not quite as bad as all that, because if you just care about the peak being clean, in other words, if you just care about this peak not getting infected by this person's, the center of this person's peak not being affected by any of this person's peak, then you only need 2 bins of separation, and then you only need 80-ish hertz of separation to use a 1024 point FFT and see it. But that's fine for analysis. That's not good for resynthesis. For analysis, you just look at assuming you can find where the peaks are at all, you just look right at the peak, and that tells you everything you know about the signal, sort of, not really, but we pretend it does. If you want to resynthesize, you probably need the entire peak there to resynthesize for you. Because if you try to shave off the parts that aren't the center of the peak, if it's a sinusoid, you can get away with it maybe, but if it's not a sinusoid, you're going to have crazy artifacts, and that's a thing.
Wait, so in the resynthesis for each bin, there's 4 components to that?
Yeah,
Okay.
and that's why the phase vocoder sounds phasey. It's because you hear the beating between those 4 oscillators because they never really quite tune up correctly. So that's the business about window design, and using windows to try to analyze sounds. Now, just to go back, the whole point there was there's an assumption that the signal that we're looking at actually can be modeled approximately as the sum of sinusoids. Right? If the signal doesn't consist of a bunch of sinusoids, then this particular analysis you'd have to change radically. Like if you were using this to analyze noise, I think you have to think radically differently about that than how you would think about using it to analyze a sinusoid. So really, mostly I've been tacitly assuming that we're messing with sinusoids. I think only because historically that's the way people think about radar and other things that people have tried to analyze in the past. And if you're trying to analyze noisy sounds, I don't think there's much in the literature that says what happens when you go analyzing noise with windowed FFTs. Which is too bad because, in fact, lots of interesting sounds are noisy. And if it's sort of maybe partly pitched and partly noisy, then who knows? And the engineers will just tell you, yeah, well, what's your model? And you say, well, there's no model, it's the sound I've got. And then you sort of end up just playing blind man's bluff with the thing, or rather messing with it until you get a good sound, however you might be able to do it. So that's kind of the story with that. Questions about all this? I'm giving you much too much information. Yeah?
Is that on that real and imaginary
Oh.
chart right there?
Mhm.
Is the amplitudes are negative? Just to clarify, like south of the
Oh.
line, those are negative?
Yeah, I mean, one way of saying that is think of these two things as two axes. This is the real axis and this is the imaginary axis. And both of them can be positive and negative. But in fact, in complex land, things have phases, and complex and negative are special cases of the real phase that you have. So really, the way you might want to visualize this is that this real and this imaginary part is a point somewhere in the complex plane, and then something that, I guess it's time for another one of these things. Okay, save as, call it number D. So another way of describing these things is just not trying to make any real three-dimensional thing anymore. There's a real part and there's an imaginary part. And here's an amplitude, and here might be the amplitude at the next bin. It'll be almost, it'll be in the direction of negative whatever this thing is. But in fact, they're just some phase or other.
Oh, that's okay.
And it's even worse because then if you looked at it with continuously changing frequency rather than going through zero, it would actually spiral around. Whoops, which I can't do like that. Yeah. Now, just to go back to using this to estimate frequencies then. So this goes back to the patch that I closed out earlier. Or did I? Yeah, I did. This. So here, part of the joke in this patch was that this phase difference as it was moving around was actually a good measure of the frequency of the oscillator that I was plugging in. So if I just turn on one oscillator, and then if I look at it whoa, what is happening now? That's cool, whatever it is, but I don't know why I'm seeing what I'm seeing. Oh, 300, okay, 440, 439.8. There we go. All right, so now what we're seeing is I just told this oscillator not to be exactly at the frequency of this oscillator. And so this is simulating what would happen if you took the sinusoid and put it into a Fourier analysis, or a sequence of Fourier analysis windows to try to guess what the frequency would be. Right? And so the answer is going to be something like, well, we know approximately the frequency because approximately it should be the frequency that we're looking at. In other words, if we see energy in a bin of the Fourier analysis, then we should assume that the frequency that we're looking at is something not too far from that bin. How far? Well, how far is given by the Hahn window bandwidth, which is plus or minus 2 bins. So if we're looking at energy in a bin and we're trying to guess what the frequency is, we figured, well, naturally the possible frequencies that we would consider important will be plus or minus 2 bins of the center frequency of that channel. Right? But that's pretty rough because again, if we're doing 1,000-point analyses, that's 160 hertz wide, which is an octave at middle C, say, almost an octave at middle C. So that's not, you're not talking high frequency resolution. Right? So the horrible joke is that the frequency content of a sound, as you hear it, is not present in the bin number of the FFT. That will tell you ranges of frequencies. That'll give you like whether it's high or low frequency, but that will not tell you the pitch of the sound at all. The pitch is actually encoded in this phase slippage from analysis to analysis of the sound that made it into that bin. It's constrained by what bin you're looking in, and the constraint is that it's plus or minus 2 bins of that frequency, but the actual frequency is this. It's the center frequency of the bin plus or minus whatever the frequency correction is that's told to you by this phase slippage. And that's worth actually trying to do out in equations, even though it's hideously confusing. I'll just go ahead and attack it anyway. And and this operation is called the phase vocoder. Or actually, this is the analysis step of the phase vocoder. And I'm trying mostly to talk about analysis and not very much about resynthesis, because that's not really the subject of the course. But this is one half of what you usually call the phase vocoder when you're using it to make delightful sounds. Okay, so here's what's going to happen. We're going to be looking in frequency in the neighborhood of some bin, and it's usually people use the letter K to talk about a bin. So this is the kth bin as an integer, and the frequency associated with the kth bin is 2 pi k over capital N radians per sample. Or, if you like, it is sample rate times k, times k over N cycles per second, or hertz. Okay, those are two ways of writing the same frequency. Am I doing something wrong? Well, we'll see.
It's the center position.
That's the center. Yes, thank you. That's the center position of the bin, if you like. And so now if we're looking at energy in the kth bin, we should expect the thing to be somewhere between k minus 2 and k plus 2. Because of the width of the analysis window. And if we change analysis windows, that would be some different number. Now suppose, and here's where it gets really wretchedly complicated. Or not complicated, just confusing. So now I'm going to presume that I'm going to do 2 analyses. Actually, let's, I think I can simplify it slightly by assuming that we'll do 2 analyses first that are end to end without any overlap. Okay. So now suppose we get a phase here and a phase there. These are not phases in adjoining bins like I'm representing here, but these are phases at adjoining times. So the way to think about that here is bins are like this, and time is like just different time slices that you see the same bin at. Right? So that's a different dimension. All right. So, well, what's the phase difference going to be? Well, the phase difference is going to be somewhere between plus or minus pi. But okay, so for instance, if we see a phase difference of exactly 0, then that could mean, well, that means that whatever we see here is the same thing as we see there, and so we could say, well, maybe that means we have a frequency of 0. Maybe we have a frequency of 1 in bins, because again, if I just draw a sine or a cosine, let's draw a cosine to be consistent. And I'll draw the same cosine there. Well, it's the same phase because it's the same thing. So anything that repeats from the one to the other has the same phase difference. So if I see a certain phase difference, okay, so going back.
Sorry, that's the same bin with the two instances of time?
Yes, right. So now I'll, just to cause trouble, I'll try to draw a cosine wave that has a period which is twice as big as we want. Right, like that? Well, this one has advanced 1/2 phase, sorry, 1/2 cycle of phase from the one to the other. And in fact, if I have any fractional frequency here, well, that it was a half, but in any fractional frequency at all, call it I don't know what, L, then the phase slippage will be L from the one to the next. And then if the frequency were 1 plus L, it would be the same phase slippage and so on. So here, if I see a phase slippage of L, it's going to be in cycles, so I'll see a phase slippage of, say, K plus L. Or rather, to say it again, if I saw a phase slippage of L from here to here, then I would say, yeah, okay, so L can be achieved anywhere, any multiple of K plus L. And furthermore, so that could be K plus L, or it could be K minus 1 plus L, or in fact it could be just any old NK plus L. So those numbers are separated by exactly 1 bin apiece. So the candidate frequencies for something whose phase slips L in 1 window length are spaced 1/4, well, are spaced 1 bin apart, which is 1/4 of the window size of the Hahn window. So if we do a Hahn window analysis and look at and look at it with no window overlap, and try to use phase difference to tell us what the frequency of the sound is, that gives us 4 possible candidates that it could be. How would you figure out which one of them it is? Well, okay, so the answer to that is this. Suppose I now say, okay, so usually people use capital N to talk about the size of a window. Now suppose I make there be another number which is a hop size, which is smaller than N. Well, in that case, the difference in frequency from one window to the next is not L, as it was before, which is the actual frequency of the thing, but L times H over N. In other words, it's L times whatever fraction of a window we've actually moved forward. And so to estimate the frequency again, so we find the phase here. No, wait. I'm going to do it this way. Don't know if this is a good idea now. I'm going to call this B1. So supposing A1 and A2 are the same time but different bins, but B1 is the same bin but a different time. Okay, and suppose this is now H later. Well, this phase difference here, which I'm going to call phi, is the amount of phase that it changed from the analysis here to the analysis there. So this is just one bin now. This whatever we're talking about here is now repeated for every single bin of the analysis. And so this is now so a frequency of L would give us L H over N. So our analysis of the frequency would be phi times N over H to correct for that factor. Plus, and then that could be plus or minus any number of cycles, right? So it's actually, I should draw it that way then. Sorry. Now I need another variable name, so let's call it M. Okay, so if the angle is phi, the frequency estimate is phi plus any integer, because it, in cycles, not in radians. So this is so pretend phi is not the angle, but is the angle in cycles. So it's actually the angle divided by 2 pi, which I could put in, but then it's going to get confusing over here. Okay, So whatever m is gives us gives us a different estimate for the frequency, and that frequency could be 5 plus 1, 5 plus 2, etc. times n over h. So these things are actually spaced. If we regard this as a set, but it's a set of numbers, so we can draw it on a number line. Phi will appear, but also will appear phi plus, phi n over h, sorry. But also phi, which is some frequency, and the same frequency plus n over h is the next one. And so the distance between these two is n over h. And so what we'll get is estimates which are spaced n over h steps apiece. Here, when we jumped an entire window, the estimates were spaced one bin apart, and that agrees with what we have here, because n over h is in that case 1, because we set the hop size equal to the window size. And then we got all these ghost images. If we make h smaller than the window, then n over h is bigger than 1, and then these estimates are more widely spaced. And in particular, if we set h to be n over 4, then n over h is 4, and then whatever estimate we get, the next estimates over will be 4 bins away at least, and therefore will be out of the interval. And for that reason, if you have a hop size of no more than 4 times the window size, then you can get a single valued deterministic estimate of the frequency of the sound using phase difference. So you have to use both a knowledge of what bin you're in and also a knowledge of what the phase change was. And you have to find the integer m that you add to the number of cycles to the phase that it slipped that gets you within 2 plus or minus 2 bins of the center frequency that you're looking at. And every once in a while, especially if you're looking at a noisy signal, and if you're using a small hop size, it actually can give you a value that's impossible. And if that happens, you just say, no good. The analysis was no good in this channel. We'll just blank it out for that cycle, or for that analysis. But you want for there to be a maximum of one possible value. This is what's called phase wrapping. And you can make it very complicated by thinking about wrapping the phase around around this picture of the complex plane. But it's much, much simpler to think about it just in terms of this aliasing. And this, by the way, might remind you of what you saw in elementary school when someone took a diffraction grating and threw a laser through it. This is exactly the laser through the diffraction grating effect. It's the same thing. The same phenomenon. So it's hard to write a formula for this because you have to use you have to make up a round function and so on like that. But it's easier just to describe it in terms of what it is exponentially, which is the frequency estimate is the one of these numbers that is closest to k. And figure what m is out by solving for m and then finding the nearest integer to that solution. Oh yeah, so I mentioned that this hop size should be no more than a quarter of the window size to get unique valued frequency estimates. That's true if you use the Hahn window, but of course there are snazzier windows that have other widths for which that number changes. But at any rate, you almost never want to use less than a quarter of a window hop. And in fact, classically in the phase vocoder, people used an eighth, which I guess was just to be super safe. And the phase vocoder that comes with PD, since I wrote it on a 25 megahertz machine, I just used 4, but you probably should use 8 to get a better sound. All right, questions about all this? So I actually made a patch to do this, which grabbed the values out of the FFT and applied arctangent to it and then tried to guess the frequency, but I'm not going to inflict that on you because I'm not sure I'll be able to remember how it works. But you can do this, and what you get is an estimate for every single frequency, for every single bin of the Fourier transform. And then you got the next step. Then is probably going to be something like, well, which of those are real, or which of those if I want a list of 10 numbers which are the most important sinusoids present in a sound, what do I do? And the answer usually is a two-step answer. The first thing you do is you go back and you get a nice windowed FFT, and you find all the peaks. And to be able to find all the peaks, you probably need to get the magnitude of the FFT, and you need for these things to be at least 2, and in practice a little bit more than 2 bins apart from each other for you to even be able to resolve these peaks from each other. In practice, 2.5 or 3. And then once you know what the peaks are, what you do is you look at the place where the energy is the highest, the best bin you got, and then you use this phase measurement in order to try to figure out what the accurate frequency estimate is for that, for the peak, for the sinusoid that you presume is there. And things happen. Of course, the sinusoid probably is changing in frequency and in amplitude in time, and therefore you won't get such a perfect shaped peak. In fact, if the thing is moving quickly up and down in frequency, this peak will be widened artificially, and then you'll have more trouble resolving the frequencies than you even should have in theory. Yeah. Oh, the other thing about that is, how do you guess what the amplitude of the thing is? Actually, there are 2 more things to say. One is, how do you get the amplitude? The answer to that is, at least the answer that I think is the best, is this. You go back to this, oops, go back a couple of pictures now. Can I get back to a previous picture? Go back to this picture, which gives you the Hahn window shape, which is this plus ripples. And of course, you only get to see it at the bin frequencies. But you go grab a bin frequency and I'm sorry, yeah, right. I guess I'm drawing it here as if these are the bin frequencies, and this is the true frequency, right? So you go look at the bin that's closest to it, and that gives you an approximation of the amplitude, but that is going to be off by however much this window is down from the maximum. And the way I've drawn it, it looks pretty minor, but this could be as much as a half a bin off, which is like, I think it's something like 70%. So 30% less amplitude than at the very middle. So you can cheat. If you believe you know the frequency, you take that amplitude and you divide it by a formulaic number, which is just what this window shape actually is. So this window is a combination of 3 of these sinh functions. These things. It's this minus a half sine pi f plus 1 over pi f plus 1 minus a half times the other one with f minus 1. That's just a formula. You can actually write that down as a function in any language you want. And then you can just apply that formula for whatever the frequency deviation is that you believe you saw. And that will give you a correction factor that gives you the accurate amplitude of the peak. Some intuition tells me that really what you should do is make some kind of a weighted average of all 4 of these. But I've never been able to figure out a principled way to do that, and so I just don't know what you can do that's better than just look at the best point and then guess from there. And in practice, it seems like that doesn't work too badly. So it's interesting. The frequency estimate is actually a much more solid idea than the amplitude estimate. So go figure.
The weighted average would be something similar, like a centroid, but within the frequency band, or it's something different?
Well, it would be something times instead of just multiplying the nearest by some fudge factor to get there, you would multiply this by something and this by something and this by something. In fact, each of these gives you an estimate. But these estimates are probably not very reliable, and these estimates are probably pretty reliable. So I would maybe take the average of these two. But if this one's real close and this one's not so close, then I would weight this one more heavily. So I'd multiply this one by 70%, that one by 30% or something. I don't know. But someone could write a paper about this, or maybe this paper has already been written, I just haven't seen it, about what the optimal way of doing this would be. And then you would have to impose a model like, yeah, and this is for finding sinusoids in noise, or this is for finding sinusoids with other sinusoids interfering or something like that. And there was one other tiny detail to mention. What was it? Let's get back to D. Well, maybe that's it. I'm feeling guilty about not having put that 2 pi in there. Where was that? Oh, that was there. Okay. All right. That was real technical. Okay, so the only other thing to do really about Fourier-based analysis is to enjoy the wonderful Sigmund object and how you can use it to drive sinusoids and try to figure out what pitches are present in sounds and things like that. But I will do a little bit of that next time because there's not enough energy left in the room, even in my brain, to go charging into that now. I'm hoping next week some of you will have cricket attempts, and if you are willing to show them in class, that would be great, because that will tell me what kinds of things I should be talking about in order to get you where you're going. And again, I'm totally agnostic as to what analysis technique you want to use for figuring out how to make a nice cricket. Just do whatever appears to be good. And I'll tell you, what I did was really slummy, so don't be afraid to be slummy. By slummy, I mean don't take something out of a journal and try to re-implement it. Just look at the thing and figure out what it is. apply brains as well as technique. It actually, yeah, it sounds like it should be easy to make, but it turns out to be not so easy as all that. Okay, so see you next week. And yeah, so we only have like, even including finals, there are only like 9 sessions, so we'll it'll be a light quarter. There'll be a lot of time to think about stuff.